So this video is to demonstrate an entirely open source, complete emergency respirator machine built around a BVM, or also known as an ambu bag, and that can be made for a very low cost of around $100 complete machine. So it's designed to fulfill the requirement for such device so that it can be adequate for treating COVID-19 patients. To be useful, it needs to implement several important features. It needs to allow the constant volume and constant pressure mode, variable speed, variable inspiration-expiration ratio, alarms, and offer the patient assisted breathing mode, where the machine can detect when the patient voluntarily stops breathing to trigger an assisted cycle. If the patient doesn't breathe, then after a programmable time, the machine will force the cycle and issue an apnea alarm if needed. For the machine to be useful, the BVM itself needs to have certain features. And I use a BVM that's from Carestream Medical. It's very common in Canadian hospital, and by the way, thanks to the Rosemont Hospital in Montreal, who gave me the one that I'm using today. First, it needs to have an exhaust that is not discharging ambient air, but can be connected to an evacuation tube, as you can see here. This is important both to avoid spreading contaminated air from the patient and to allow installation of a PEEP valve, as this positive pressure is important for proper treatment. The second feature is the pressure relief. The pressure relief, it's a valve that opens at 40 centimeter H2O, and it provides an important safety in case anything goes wrong with the machine. So it's very important to have it. And the third one is the convenient port here where the pressure sensor is connected. You will see how it's made a bit later. So let's see how it works. So here are the parameters. We're going to start it like this. So here you have the speed, you have the volume, and you have the pressure. As it runs, you see here the movement of the bag is shown on this graphic. Here you have SP, that's the actual speed. The PEEP and the PEEP pressure are all zero because here it is not connected. And you have the volume, that's 677 and 680 have been programmed. So you can see the different adjustments. Here you have the rate, so we can make it go a little bit faster. Okay, it's quite fast like this. After that, we can set the volume, so it can go for a smaller stroke. Or even smaller than this. Or we can restore it to the value it had. I think it was 680, so it can go a bit higher than this. Then we have the pressure. It's 46 centimeter of H2O. Then we have the PEEP pressure, so you will have an alarm if the pressure at the end of the cycle is lower than this. This is useful to adjust the PEEP valve and make sure that it stays adjusted. Here you have the synchronization. It's in percentage of the total time of the cycle. and it means that it's going to wait at the end of the cycle. So if we put it to a higher value, let's say 50%, it will wait before it starts doing another cycle. So in the meantime, while it's waiting, the patient can trigger it. Okay, put to 0, so it's only automatic in this mode. Here you have the inspiration-expiration ratio, so it can be from 1 to 3. Here you have the apnea alarm. This is done to detect when in patient-assisted mode, the patient has not taken a breath by himself for quite a while. Here you have the ability to save all the setup value. If you save the value while the machine is running, if there is a power loss, when the power recovers, the machine will automatically start again. So if we press for a long time, we have the stop, you saw it here, and then it will say that it can start. You can be either in PC mode or you can be in VC mode, pressure or volume control. So the machine runs completely autonomously, and if you want, you can also connect it to a laptop, and you will have the ability to see the waveform. So the waveform that you see here is the pressure. You have the commanded position of the motor, the real position of the motor, and the phase indicator here. The balloon is fitted, and we restart the machine, and we see that it stops in a very different way. So it makes some noise. It's normal. On a final machine, the motor would be dampened and you wouldn't see that. As I said, it's entirely open source, and I designed it to use almost only off-the-shelf parts that are both ubiquitous and affordable. So first, the controller itself, it's an Arduino Nano. It's extremely common. It can be found very cheap. It's a 328 processor. It's more than powerful enough to both control the machine, its keyboard, and its display. I wrote the complete software using Arduino, as it's the most ubiquitous toolchain, despite its shortcomings, and it uses non-third-party open source libraries. As of now, there is a configuration parameter file that is separated from the code, and it allows you to get the newer version and without losing your configuration. And here you have the code. To sense the pressure, the controller uses either differential pressure sensor or two pressure sensors like this one that are absolute pressure sensors. So I use the BMP 180 or BMP 280, and they are widely available either as a chip or pre-built module. As you've seen, there is a 2-line LCD display and 5 buttons. There's also an alarm buzzer here, and I plan to add the separate LED for visual alarm. The mechanical part uses a stepper motor for precise move with enough torque to compress the BVM even at the highest volume, the highest speed and pressure. The part that compress the bag itself are shaped to deform as gently as a human user would. They are round, as you can see. It's done to extract as much air as possible while not prematurely damaging or wearing the BVM. So you can see it here. The two vertical pillars that you can see here are here to ensure that the movement on both sides is symmetric, regular and orderly, but they are not what drives the mechanism. As you can see here, there is a 1-inch nylon or polyester webbing that's found in regular ratchet straps. They're very strong and resistant to abrasion, and that's what is used to transmit the force from the motor. Now I can turn it so we can see under the hood. As you can see, the stepper motor used is powerful enough. It's an EMA 23. It's got 3 Newton meter torque and 5 amps current, so it's one of the bigger you can find. It's driven by a standard controller here. The required model should be able to deliver 5 amps and use up to 48 volt. The one I'm using is a lead shine model. A DM556 would be adequate. This one is bigger, but that's what I had. The power supply here, it is 36 volt, 4 amps. It's 150 watts. And you should take a better brand than this one. I recommend using Meanwell power supply. They are reputable and you won't have problem with this. As you can see, the strap goes through this 8 millimeter or that's 5/16 of an inch aluminum part that had a slot cut into it. You can see it here, it's the same part. And the strap is held in place with a 3D printed shim, and there are 2 set screws. So the aluminum part is supported by a very common skateboard bearing that's inside here. In the final design, it should be placed between 2 bearings, not just one like here, and the strap will then turn on each side on these 3D printed rollers that also use skate bearings. So as the motor turns, you will have both straps that will move in opposite direction, pushing the bed simultaneously on both sides. It's a very simple mechanism that's strong and energy efficient. With a 3 Newton motor and a 24 millimeter diameter when it's fully wound, it can exert a total force of 25 kilograms or 55 pounds. So let's see it working. As you can see, it's very simple move. So the BVM itself provide for the return force so that the part will go up. There is nothing in the mechanism that forces it to go up. You will find all the STL and the CAD file for all the printed part on the GitHub site. This device have yet to be tested and certified in a hospital setting, and as such, it should only be used for prototype and experimentation and should never be hooked to a patient. The whole project is released under General Public License, the GPL version 3, and all the program and CAD files for this design are and will remain freely available. As of now, that's where the project is, and I think it's pretty close to a usable machine, and everyone who's willing to participate is welcome. The next step will be little details that need to be worked on, and then medical testing and review. If you think you can participate with the medical assessment, the regulatory process, improvement, if you have idea, or if you are interested in getting ready for manufacturing it once it's approved, you are more than welcome to contact me. Be well and take care.